Okay.
Yeah, I'm happy to announce the next speaker. It's Pierre Lochak, and he'll talk about the Grothendieck-Teichmüller theory.
Okay. Let's say, more modestly, let's call it, I don't know, first inputs in...
Changing the title word?
No, in Grothendieck-Teichmüller theory. Okay, so, well, I've been assigned the task to introduce Grothendieck-Teichmüller theory, which is not an obvious thing to do. So I thought about how to present things, and I still think, historically speaking, I mean, to have some bits and pieces of history would be really interesting. It's a very short history. So at variance with the other speakers, I'll start with references. The references are not for the sake of references. They are just the four, well, I maybe hesitate to say most important, the four pioneering papers, and they still determine to a large extent some versions of the theory. So the first is Grothendieck, esquisse d'un programme, sketch of a program, esquisse d'un programme. And well, I won't give the precise references. The point is to comment on these references. 1983, then you have Yasutaka Hihara. I can't remember the title. It's basically profinite braids and something, so it's Annals 1986. Then you have, of course, Drinfeld, famous paper. Then it's, I don't know, it's Leningrad Journal of Math. Yeah, I have it here. So it's a long title that you've all seen probably. So it's on quasi-triangular, etc. And it's 1989. And the last one is the Ligne, P1 minus 3 points. It's MSRI 1990. So they're very, I mean, they're just a few years apart, and even the writing may be not, I mean, these are the dates of publication, or except for this one. And, okay, now I write 3 messages, which I'll try to, let's say, explain or detail. So the first message is large Galois representations, which is a slightly outmoded way of putting it, but it's the way Hihara used to call them. Large Galois representations are often faithful. The second is, I think, the key idea of the esquisse, which makes Grothendieck-Teichmüller theory possible at all, is the two-level principle. Well, in French, principe des deux premiers étages. Des deux premiers étages. I write it in French because I think, well, maybe I should say that all 4 papers make astonishing reading, right? I mean, they're 25 years old, but they make astonishing reading. If you read all of them, you will know much more than I do about Grothendieck-Teichmüller theory. Okay, and the third is the theory, and this one is, I'll explain. This one is slightly more personal, if you want. The theory is, or should be, nonlinear. And I'll try to explain what this means. This is not really personal, this is Grothendieck's idea, original idea. Maybe I should say that what we've seen, I mean, whenever the Grothendieck-Teichmüller group was evoked this morning, it was what I would call genus 0 pro-unipotent. And this is not quite as nonlinear as Grothendieck would have liked it. So nonlinear means, well, don't scream, non-motivic. So maybe I should say that when Grothendieck in the Esquisse d'un Programme, when he writes about Grothendieck-Teichmüller, it's really distinct from motives. It really says it. So what does it mean, distinct from motives? It simply means you take into account the full profinite completion. Motives are about the pro-unipotent and pro-nilpotent completion of the Galois group, and maybe I'll return to that, I hope. And the original idea of Grothendieck is really full profinite. So it cannot be motivic. But of course, I mean, partly because of that paper, motives have entered the game and very successfully so. And many ways also here, many ways of linearizing things have proved, of course, very useful and efficient, but still, in some sense, and I'll explain this, and actually we've done things along this line, even some time ago, which also explain why I will put two more. Oh, no. I leave this here, okay, for the moment. Okay, so what's the general theme? The general theme is, at first, in the daydreaming of Grothendieck esquisse, the thing was to produce a geometric description of the arithmetic Galois group of the rationals of GQ. And at that time, he was very much struck by Bieli's theorem. So maybe I should recall what Bieli's theorem says. Because so Bieli's theorem says, so Bieli's theorem says, so it's around 1976. So any curve, any smooth curve x over defined over Q bar. So it's an over Q bar, can be realized as a covering of P1 ramified over at most 3 points. So, which you can take to be 0, 1, and infinity by rigidity. Okay, so the converse thing that so if you puncture your curve, so after puncturing the curve over on the fibers of these 3 points, then you get an état cover of P1 minus 3 points. And then the fact that any état cover of P1 minus 3 points is defined over Q bar is quote, a well-known fact. It's a Gaga-type theorem. But the surprise came from this. This is a dream theorem because the proof is 2-page long and completely elementary, and it's something that almost changed not changed the course of certain subject, but yes, well, it had a tremendous influence. Okay, anyway, so that will take care of this, of the first thing. Why? Okay, why? So I explained the first message, which was received by Grothendieck around 1980. Just after Bieli proved his theorem. So what is the first message? The first message says the following: if I take x, well, I have to recall a little bit about SGA1, the outer Galois action on fundamental groups. So in SGA1, SGA1 will tell you that if I have an x, which is what? Which is a geometrically connected scheme over, well, it could be a stack anyway, over a field K. Okay. Then if you put pi1 geom with the geometric pi1 of x will be by definition pi1 of x tensor k bar. So when you extend the scalar to an algebraic or inseparable closure, and then so to say it's geometrically connected, say that this object is geometrically is connected, and then you have this exact sequence. Okay, so this is really the fundamental sequence of. So this is the absolute Galois group of K, which you can also write, if you want to make it into a fundamental group this way. And if you're an algebraic topologist, this reminds you of the fact that pi 2 of spec k is trivial, and this can be viewed as a long homotopy sequence, except it's short because pi 2 is 1. Okay, so you have this thing, and very shortly we will explore the case x equals p1 minus 3 points. So the 3 points now equals 0, 1, and this I will baptize p star. Some people do it. I mean, it's just not to write p1 minus 0, 1 infinity all the time. So this sequence gives you, so I write it this gk just for simplicity. So formally, this gives you an outer action on this. Okay, so for any, okay, so I'm really streamlining everything, which means I don't put base points, for instance. I don't put base points because you don't need to, because there's an out here. Well, anyway, yeah, okay. And there are many things you can say. There are 500 pages you can say, but okay. So I just do this. And what? Oh, yeah. And now you return to Bailey theorem, and you say, and you find that if x equals p star and k equals q, then, so this is what I call large Galois representation. Now I would call it an outer action, okay? An outer action of the arithmetic Galois group on the geometric fundamental group. Now have this. If, so proposition, or say corollary to Bailey theorem. Corollary, I'm really bad at numbers. Even in French. Corollary. So for x equals this is injective. Okay, this map is injective. GQ to out p star is injective. So. So basically it says that, I mean, this is not difficult to prove, I'm not going to into it, but this is really an easy corollary of this. You can think of elliptic curves. Take elliptic curves, you can realize all elliptic curves for all J invariants which are algebraic as covering of p1 minus 3 points, and then since you can realize all of them, then something we would be in the kernel of this would essentially act trivially on all the J's, and since all the J's are all the algebraic number, it would be trivial. So that's it. So that's okay. That made a tremendous impression on Grothendieck, who was used well, and for good reasons to Galois representation on cohomology groups, which are not faithful, of course, and also on Hihara, who undertook to.
Sorry, did you lose pi 1 somewhere?
Yes, I did lose pi 1. Very bad. This is absolutely a free group on 2 generated. That's what I'm going to detail this. Okay. So
should I have known that fact that the Galois group, the outer Galois group Q acts on the free group of 2 generators?
Should you have known that? I don't know.
I mean, by some other means.
By some other means. No, I mean well, but this is not the free group. This is the pro-finite completion, of course.
Oh, yeah, okay.
Of course.
Okay.
Completions. That's a very good misunderstanding. Sort of misunderstanding. No, because this program will of course be about bringing people together, and completions are absolutely crucial, of course. I mean, it's just as simple as auth of f2 is GL2z, okay? And auth of f2 hat is just, Grothendieck calls it monstrous. Monstrous.
F2
Okay.
is not GL2z, only if it is abelian.
Sorry?
F2 is not abelian.
F2 is not abelian, no, but still, the automorphisms of f2, of outer automorphisms of f2, are still GL2z. That's a theorem. That's not completely obvious. The very old theorem. The outer automorphisms of f2 are all given by just automorphism of the abelian group, of the abelianization.
Okay.
That's wrong. That's completely wrong if I change 2 into 3.
Yeah.
Yeah, totally wrong if I change 2. This is totally specific of 2. Okay. This is a good, I mean, this is monstrous. So, I mean, that's Grothendieck calls it a monster. But the GT hat will live in this group, okay? So what we've just seen is that GQ lived in this group. Well, you can ask me why I put alt and not out. I could put both. The fact is that this sequence has splittings. It splits over any rational point. So if you have a rational point here, if you have a rational point of k, it gives you a splitting of this sequence. There is a famous conjecture, section conjecture by Grothendieck, which tells you that the opposite is true under certain conditions. Okay. Sorry, I'm trying to stick to, some principles because it's very easy to deviate. Okay, so what was I going to say? Okay, so that's the first thing. And now, so now we're going to study. So, Grothendieck-Teichmüller theory, which was interwoven with Abelian geometry in Grothendieck's esquisse and letters to Faltings, is very much about pi1. Okay, pi1 is the only non-Abelian invariant we know, and maybe I'm wrong, but you know. It's close to being the only non-Abelian invariant we have. And so Grothendieck-Teichmüller theory is about pi1, and so is Abelian geometry, and so is the section conjecture. Now, if you're speaking about pi1, about the fundamental group, what will be the main objects? So the main object of the theory, whose goal I've not really defined yet, and there is no goal in some sense. Yeah, I've given one goal, and the goal is to find things around. So one thing is, so if you have pi1, then you can imagine that some of the main object will be in dimension 0 the field, by definition, in dimension 1 the curves, in dimension 2 surfaces, so tautologically, and then in some sense that's it, because you have Lefschetz hyperplane theorem, which tells you that if you have something which is a dimension bigger than 2, then you can cut through a hyperplane and generically you get the same pi1. So why bother? And here even surfaces are very often fibered over curves, or stable fibration over curve. So curves are really a determining object, but you also have k pi1s, which I forgot. No, I didn't forget. That's the k pi1s are by definition determined by their pi1s. Okay, so among the k pi1s.
So sorry, what is k pi1?
K pi1 is a space whose the universal cover is contractible. So it has only pi1. Okay, all the higher homotopy group vanish. So basically, once you've okay, so k pi1s. And then I'll talk about which k pi1s you want have been studied, or some have not. And now, since everything is going very fast, time is flying. I will return to P1 minus 3 points and just detail this map. Okay? This map. So,
you didn't finish your sentence about k pi1s?
Sorry?
What was the point about the k pi1s?
Well, the things which are naturally entering the theory.
Oh, okay.
So maybe I can, I'll have a list of k pi1s. Basically, hyperplane arrangement, moduli stacks of curves, and yeah, and configuration spaces. Maybe I can put it here. Moduli stacks of curves. Hyperplane arrangements. And configuration spaces, which are not very, very different. These are, but okay, I'm still into trying to get to this. This, I think, may be the key, again, the key idea of the esquisse, which again makes Grothendieck theory, Grothendieck-Teichmüller theory just possible. Okay, now P1 minus 3 point Gauss action on P1 minus 3 points. Gauss action on P1 minus 3 points. So this is very nicely explained, I mean, in many places, of course, but Hihara explained it especially carefully. So you put it this way. Again, I have to be brief. So you have 0, 1. Infinity is at infinity. Then I take Hihara's notation. So, okay. So I won't bother you too much with groupoids, tangential base points, and so on. So, but you have to a little bit. So P will be the interval between 0 and 1. So it's not a fundamental group, it's a fundamental groupoid. And since 0 and 1 are missing, here you have a point, you have what is called a tangential base point, which is 0, 1. And here you have called 1, 0. And if you were an analyst in the 19th century, you would say you make a cut here. Make a cut here, so that makes the neighborhood of 0 and 1 simply connected, and then you can base your pi1 at these region and denote them by little arrows. Okay, so P goes from 0, 1 to 1, 0. And then you have a little circle which goes like this. Oh, no, I'll make it simpler. 0, 1. I do the full circle, okay. Just to make it simple. So x from 0, 1 to 0 to itself. And then that's it. That's it. I write this. But okay, the isomorphism group of this over anything is generated by, it is S3, okay? Generated by theta omega. Theta is order 2, so t is the running variable. Omega is order 3, okay? So theta is just a mirror, and omega is an order 3 thing, mapping 0 to 1 and 1 to infinity, shifting things. So this is theta of x, okay? And now, so now let's try. So you take sigma, an element of the Galois group, and you ask yourself, what are sigma of x and sigma of p? Why sigma of x and sigma of p? Because I'll write y, let's say y will be p minus 1 theta p, theta of xp. So you do this, this, and this. So p1 of p star based at, no, sorry, not based, based at 0.01 is xy, the free group. So let's call it p1, topological pi1. Okay? So this is your free group on 2 generated. Okay? So if we compute sigma of x, sigma of p, we'll have computing actually more. Now, sigma of x is quite easy. So sigma of x is just x to the chi of sigma, where chi is the cyclotomic character. So y, maybe it would be a little I mean, it would take 5 minutes to explain, but it's really important because it gives you a feel of what we're actually doing. let me try to, okay, so sigma of x is attached to simply p1 minus 2 points, which some people call GM. I mean p1 minus 0 and 1, okay? So this is computable. This is it. How do you see that? Well, maybe, oh, that's okay. How do you see this fact? You see, you return to your sequence. Let me try to explain what this means. I mean, sigma. What is sigma of gamma? How do you compute sigma of gamma? Sigma of gamma, by definition.
What is gamma?
Sorry, gamma is any loop, any path even, between the base points of the groupoid. Okay, I have a groupoid with 6 base points, 1 here, 1 here, 1 here, 1 here, and the same at infinity. And I'm trying to, but that would, what I'm saying would do on any variety, blah, blah, blah. So what is sigma of gamma? By definition, it's sigma minus 1 gamma sigma. So how can you compute that?
Because sigma is an element of G group.
Sigma is an element of the Galois group.
Yeah, but so how can it act? What is the multiplication? Is it the composition or what is it?
Yeah. Let me. Okay. Yeah. It's a bit long to justify. So I'll show you how you can see it literally with the trick of a nice way of saying it by that Hihara likes. Take a cover x of p1 minus 3 points, okay? And take a function on that cover, okay? And take something and take a germ of function, okay? Then call it phi, and the germ will be a Puiseux series, okay? Some and let's say the covering as degree whatever. This, okay? This you can write the germ of your function near this on the covering x, okay? So when you do sigma, you simply apply these things. You simply apply sigma to the coefficient. Okay, I agree. I'm giving you a recipe, but it's very telling, I think. So now you do gamma. What?
Where do these coefficients live?
They live in Cuba. Then you do gamma, which is you take the analytic continuation along gamma. Okay? So you have a germ. No, real path, just topological path. Gamma can be x, y, p, or whatever. Okay? So gamma. So you take the analytic continuation, which I'll do now, and then you end up. Then you do sigma to minus 1. Get another germ. You get sigma to minus 1 by applying sigma to minus 1 to the coefficients, and then you get sigma of phi. This is how it acts on functions. And if you know how it acts on functions, then you will know how it acts on the path itself. Okay, now this will never work in the sense that you will never be able to compute it except for x. So let's do it for x. If you do it for x, then what happens?
Sorry, doesn't your definition there somewhat depend on what you choose your cover to be?
Yeah, sure. Of course, you have to do it for all the covers. Ideally, you do it for all the covers. So you do it for all the covers, and you hope that this thing will be a function of this. This will be a function of phi, which you can recognize. Usually, there's no hope that you will be able to compute anything.
But where the cover enters? Because here you just take a germ on type 1.
Oh, here, when you do the analytic continuation along x. Okay, you analytically continue. Suppose gamma is a loop, so you go from that place to the other. Suppose gamma is a loop, so you continue. And, okay. So suppose gamma is x. So what happens? If gamma is x, well, you simply change.
Sorry, I don't know what you mean by doing the analytic which you mentioned here.
Well, let me do it. Let me do it for x. What happens when you do x, when you turn around? You simply change t to e to the 2 pi I t. T e to the 2 I pi. Okay? N over d. Okay? Okay? So now if I denote zeta to be, if I write zeta to be e to the 2I pi over d, okay? To be a primitive d fruit of unity, then this will be the sum over n positive of sigma n, zeta to the n, t to the n over d. Okay? Now I apply sigma to the minus 1. Sigma to the minus 1. What I recover is the sum of an. I like this computation because this is one of the only computation you can actually make. You just see it. Of course, there are many more computations when you linearize things, and that's the good thing about linearization. Okay, so you recover an, and then you have the sigma of zeta, but sigma of zeta by definition is zeta to the n pi of sigma. And then you have this. And here you see that had I done only x instead of all this, I would get the exact same thing with this. Okay? If I do x without, if I forget about sigma, okay? We agree that x of t to the n over d will be zeta t to the n over d. Okay? So what we did, what we get is this factor instead of zeta of n. And that proves this. We just proved this. Okay? Okay or not okay, maybe if you want to see that in detail, the papers by Yara, or we also wrote a paper a long time ago trying to explain these things. Of course, there are many things you're supposed to say if you do this computation. Chi is but this computation is basic. Is right, just completely right, and that proved this.
And the point is that it makes sense only in the completion, because chi of sigma is not an errotic.
Of course, chi of sigma. When I for a given cover is a completely, or a chi lives in a z of the chi I'm using here. The chi of sigma I'm using here is just the projection, so it lives in there, in here. Okay, so it's I'm using a finite projection of it. But then when I take all covers and blah blah, then I recover a chi which lives, the real chi of sigma, which lives in z hat cross. Yeah. So here I recover a finite projection. So what you do is you compute in a finite projection, and then you lift to the whole tower, and that.
So when you write chi x power chi sigma is a
chi sigma is
completion
here.
of z, so it makes sense only because you have completed.
Sure. It makes sense that, it's here in the same, yeah.
What you're doing up there is giving us all the projection onto all the finite groups, finite quotients.
Yes,
Yeah.
absolutely.
Right, okay.
Okay, and now what is sigma of p? Well, nobody knows. Nobody knows. Nobody knows in the sense that there is no hope to give an explicit answer. So you just baptize it, and you call it this way. So this is a name. So where does it live? What is it? So what you know is that sigma of p will be, I should say, a pro-path, which is a path in the in the universal cover of this. So a universal cover in algebraic geometry is actually how do you call it? A tower of objects. And so this lives in, this is a propath which joins this and this. Why? Because these two things are defined over Q, so they don't move. Okay? So you can certainly write it this way, where P is P, and this is a pro loop. It goes from 0, 1 to 0, 1. So this lives in F2 hat. in this, well, in the completion, okay? And why do I write f sigma of xy? This is a symbol for the time being. It's to say that it's a function of x and y. Okay, right now it's not useful. I can also call it f sigma. It's just an element of this. If I emphasize that it's a function of x and y, it's because when you're allowed to play around with morphisms and take pullbacks and so on. Okay, so you have this, and these are the two parameters of the action of the Galois group, and will be the two parameters of the Grothendieck-Teichmüller group. Right. Okay, so that was much too long, of course. Much too long. Or too short. Well, it was both too short and too long. Okay. So we have, what have we done? We have the Galois action on P1 minus 3 points with these formula. And well, maybe I want to write this formula differently. This formula, you can write sigma p, the commutator of sigma and p equals f sigma. Commutator of sigma and p, because this is p to the minus 1, sigma minus 1, sigma p. So it tells you that sigma, this is very nice, very, I think, suggestive. It tells you that the commutator of the Galois action with the analytic continuation along the unit segment is the main parameter of the action of the Galois group. So this is one way to see it. Now, why P1 minus 3 points? Why P1 minus 3 points? Why P1 minus 3 points? So I take 3. Well, so some of the why is P1 minus 3 points so important? Well, some of the characterization of P1 minus 3 points are obvious. So in topology, it has well, this chi is not chi, it's Euler characteristics. It's Euler characteristic minus 1, and that's how you build, well, I won't talk about it now, but this is very important. I mean, it connects directly to topology. So over C is rigid. Is rigid. That is, there's only one complex structure. Something which is less trivial, maybe Pierre will correct me. I like this one. That over Z, this is the only smooth hyperbolic curve. There's only one smooth hyperbolic curve over Z, and it's P1 minus 3 points. And something which is maybe more to the point, it lies at the crossroads of curves and moduli of curves, because P1 minus 0,1 infinity is isomorphic to F04, so classifying 4 points on the line. Okay. So now okay. Now we're here, and we have an injection of GQ into the outer automorphism group of F2 hat, say. Okay. Now I can put a star here. This star means inertia preserving. It means that if you have x, you have y, and you have z, such that x, y, z equals 1, then the image of x is a conjugate of x, the conjugate of the power of x. The image of y, same. The image of z, same thing. So the thing is that these pro-cyclic groups are inertia groups over your 3 points.
Sorry, could you state again?
This means that it's inertia preserving, which means it permutes the inertia groups associated to 0, 1, and infinity.
So what do you call inertia group?
let's forget about it. Okay, because it would be too long. I mean, it's really not necessary. I can even erase the stuff. Generated by the loops x over along. Yeah. This is a much more. I put this because this is a much more general statement. We know next to nothing about the Galois action on fundamental groups, but we know that it preserves inertia groups. So even in any dimension, so if you have a variety and you have a divisor, then you associate a small loop around the divisor. That's an inertia group, and the Galois action, provided everything is defined or your base group, will preserve it.
So you are fixing embedding from Q bar into C, right? So
yes.
Yeah. Otherwise.
Yeah.
So you mean that it will preserve, but it will act on it. It will preserve it globally, but it will act.
We've just seen it. We've just seen that sigma of x is x to the chi sigma. So this is the action on.
And the same on y.
And the same on y.
Z.
Oh, maybe I didn't write down the second formula. I mean, this is the formula, but from this you get that sigma of y is f sigma to the minus 1, y to the chi sigma, f sigma. Okay, immediately. So you get. So now we have your sigma of x and sigma of y. Just p is more fundamental than y.
So x, y, and z, they're special ones, are they? They're
Yes.
negative 0, 1, and infinity.
Yes, because these are, I mean, it's much too general, but these are the divisor. This is the divisor at infinity. But
should I think of them as the loops around
yes,
0, loops around
yes,
1, and loops
yes,
around infinity?
yes, yes.
Fine.
okay, so the point is, how do we start? The point is, how can we describe the image? Okay. So the first step is take P1 minus 3 points. So describe the image. The task is describe the image. So the first step is take P1 minus 3 points again, and say that GQ commutes. I mean, the action of GQ commutes with the action of the automorphism group of your object. Why? Because these automorphisms are defined over Q. I mean, it's 1 minus t and 1 over 1 minus t. You only have rational coefficients. And if you say that, you get two relations, which you all know, which are the famous, the first two relations in GQ. So this thing gives, so it gives you, so it gives you 1 f sigma of xy, f sigma of yx equals 1, and 2 f sigma of zx with z xyz equals 1, z to the this is a bit okay, I put it all the same, but it's not very useful. I mean, it's xy z to the n sigma equals 1, where chi of sigma is, it's an odd number because as a finite number. So this is the definition of m sigma. If you want to forget about m sigma, just imagine chi sigma equals 1. If you imagine chi of sigma equals 1, you're describing not the Galois group, but the Galois, the subgroup, which is the Galois group over the root of unity. Okay, so you have these two things.
The last z to the n sigma should be x to the...
Yes, sure.
Last?
Unless, yeah, of course.
No, the last.
No, the last one, yeah.
Otherwise-
The last one, yeah. No, this one and this one should be y and this one should be x. Okay, so now GT0, which is a first approximation to GT, is the set, this lambda is Greenfeld's notation. I think it should be called chi for obvious reasons, but it's called lambda, so I keep this lambda. I'm faithful for Drinfeld's paper. And so this is the lambda f, which satisfy, so such that what? Such that, well, which are in z hat cross times f2 hat. I could put a prime, but okay, I refrain. Such that 1 and 2 plus, to be honest, invertibility. This is the first time we encounter something which is much more difficult in the profinite case than in the pro-unipotent case, or unipotent or nilpotent or L-adic or whatever case. Because any element of GT, okay, any lambda f gives you, okay, this is including an odd f2 hat, okay, so this is the set of f, and then you see it's a group, you can see it's a group. So f of x will be x to the lambda, and f of y will be f minus 1 y to the lambda f. Oops. Okay.
Lambda is odd.
Sorry?
Lambda is odd.
Lambda is odd, but it has to be odd. I think for some reason, maybe lambda has to be odd.
Well, you put
Because
it
this is
upstairs.
invertible.
Yeah, I put it upstairs,
Sigma.
but yeah. Yeah, of course it's odd because it's invertible, so it's odd. I mean, it has to. It cannot.
Oh yes.
Yeah. But the thing which you cannot determine is whether this automorphism is invertible or not. So, well, you just add it. This is one tiny example, really tiny example of the fact that when you try in the profinite case, there's little you can do. Basically, if you have a formal series which starts with a non-zero term, then it's invertible. But if you're not in formal series, you don't know. So this is why I have the invertibility condition, because you can't determine it. Okay, so now, what do we do next?
Could you say what the zero is then?
Sorry.
Well, you've got GT hat.
Zero is the definition. Just, this is not GT hat because there is a pentagon missing.
Ah, I see.
So we call it
this is
GT zero.
First approximation.
Yeah, exactly.
Okay.
So what do we do next? So this is where the second principle comes in, the two-level principle. Because you can say, this was sort of known, but no, it was not known. I mean, it's, I encourage you to read, for instance, Hiara's paper, which is beautiful, essentially L-adic, but really full of stuff. But the point is, what do we do next? Next, we have to pick x's, because any x can give us restrictions on this image, because you will have, let's say it won't be the same image, but then anytime you have an x, you have GQ, you have an outer automorphism group of the geometric pi1, okay? Very often, quote, it's actually faithful, because very often, for various reasons, you can, well, not very often, I mean, that doesn't mean anything, but you can find many instances where it is faithful, but then how do you determine the image? Then you will have, maybe you'll say, okay, it commutes with the automorphisms of x, which is true if it's defined over Q, blah, 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 but you will never narrow down your image to something manageable, because you have an infinite number of x. And now the idea of this piece is to take x equals mgn for all g and all n. So where mgn is the classifying stack or space of the curves of genus G with n marked points. Well, this is still not an idea because there's still an infinite array of things. The real idea, the two-level principle. So the two-level principle, I would like to say that it's similar to something very elementary, namely if you have a CW complex, you take the two skeleton, and the pi1 depends only on the two skeleton. I don't know if this image is right or not. I mean, I've never really manage to, it's close to something like this, but I don't know how to say it really rigorously. So maybe I'll say the way Grothendieck says it in the esquisse, because it's really remarkable, and it's true. I mean, it's true, and it explains a lot of properties which have been found in some sense in slightly different contexts. Okay, what does it say in the esquisse? It says something which is, okay, you have MGN. So of course a P1 minus 3 point was again M04. And it says, so the two-level principle says, you don't have to go very high, you have to take the spaces of dimension 1 and 2. So in dimension 1, you have M04 and M11. So classifying elliptic curves. It's not very different from this viewpoint because these are the Weierstrass point of your curve. So it's not very different, these two spaces. And in dimension 2, you have M05 and M12, and again, it's not very different. So the 2 points can be made to be swapped by the involution, and they're very, very similar. And what he says is that if you study these spaces, if you study the Gauss action on this, it's the same as the whole tower. I can't explain everything. It takes a lot of time. So why does he say it? Basically, you see, basically, MGN is equal. It has a completion, which is a stable completion, minus. So it's MGN bar minus the divisor at infinity. So I'm simply saying that MGN has a completion, which is the stable completion, the Deligne-Mumford completion. Then I do this inane drawing because, well, you draw what you can. And the whole point is that the divisor at infinity is made of moduli stacks of smaller dimensions. Why? Because, for instance, I mean, here it's completely topological. By the way, this is what he was trying to explain to the first-year students in Montpellier. What I'm just saying. It was a mild success. But seriously, so if you have something of genus 3 and then you collapse it this way, then you see that in the boundary of M3 bar, for instance, you will have a copy of M21 bar cross M11. Okay? And these drawings are actually accurate, I mean, after a lot of work. But these drawings are right, I mean, so the divisor at infinity is made up of, to be honest, finite quotient and blah 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 of copies of moduli stacks of strictly lower dimensions. Until you reach this 2. What I just said is right until you reach this dimension. Then it's wrong. I mean, it's not difficult to see that then it becomes wrong because, I mean, you don't have enough dimension. So I haven't proved anything here, but I can make sense and prove what is necessary, but not now, to vindicate his phrase, which is the Teichmüller tower can be built from its first 2 levels, first 2 stories. Okay? Which means, for instance, in particular, that the Gauss action on the Teichmüller tower. So, let me use this phrase very freely because, well, I don't know, it takes a year it takes a one-term course to actually build it and define it and blah blah blah. But let's call this the modular tower. So okay, I haven't defined it. It means all the MGNs, all G, all N, with various arrows, like this one. With, for instance, this would give you an arrow from M21 into M3 bar, for instance. Okay? So you have various arrows coming from topology. Coming from topology means they are defined over Q. All these objects are defined over Q. In fact, they are defined over Z. But they are certainly defined over Q. And so you have this modular tower. And let's say very slightly informally, well, no, very informally, you have this object, which is the pi1 of these things. So pi1, the geometric pi1 of MGN is what topologists call mapping class groups or Teichmüller groups. Hat, of course. So any of these things is a completed mapping class group, and then you have tons of arrows between them, and then you have this, and then you take the outer automorphism group of this, and then you know that GQ injects in this. No, that you know, as Grothendieck says, it's already faithful at the first level, because it's faithful for 0, 4. So it's faithful at level 1, so it's even more faithful. That's not a problem. The problem is this an isomorphism. So what we know how to now we know how to describe this. This we call it gamma, double gamma, because double gamma is the notation of digamma. How do you call it? Well, this is a notation of Grothendieck for this group. Okay, this is cheating. This is wishful notation. This is wishful thinking notation. So this, we know, this is included in GT hat. Oh, sorry, I didn't even mention I didn't even say what GT hat is. GT hat is the thing is GT0 plus, so GT hat equals GT0 intersected with the pentagon. So in this context, the beautiful result of Furusho does not still apply, but we don't know whether the relation 2 is spurious or not. Okay, it might be. So Furusho's result in the linear say the pro-nilpotent context is that in fact the relation I wrote down, the number 2, is implied by the pentagon. We could say that this is just the pentagon. Oh, the pentagon is the pentagon. Oh. It's one relation which is pentagonal. And it's one relation which comes from acting on the pi1 of this. Okay? And it's pentagonal because there's a 5. No, seriously. Yeah.
The 5s are not related. They're different 5s.
Oh, no, they're not different 5s. No, they're not different 5s. That's too much to say. Okay, they're not quite the same 5. Okay. Maybe there's anyway, it's pentagonal. And, okay, so this is GT0 plus 1 relation. And here this is, and our gamma is GT plus 1 relation. Actually, it's GT intersected with one more relation, which I don't write. Yeah. But now this gamma is equal to this. Okay. So, what is the message? The message is the two-level principle enables you to actually describe this tower, the outer automorphism group of this tower. I'll finish in 3 minutes. So, pretty explicitly. Okay. So this gamma. So you have this nested sequence. GQ is included in gamma, which is included in GT hat, which is included in the automorphism group of F2 hat. Okay. So this is much bigger, but it could be that this equal that. Right. It could be that this equal this and this equal this. This equal this is very interesting because this has to do with, I say it in passing, with state things and so on, and this not. So it could be that this equal this and we don't know. It could be that this equal this, and we don't know either. But we can describe this, and maybe I'll contrast it with another result. So imagine you take instead. So here we have the modular tower, which is all the tower of the model, all the modularized towers of curves with arrows and so on. Now imagine you take all the varieties as your sample. So a fairly big sample. You need far less. Then as your category, and then on this category over Q. And then you still have this functor. And you still have the outer automorphism group of this functor. So it's the outer automorphism group of this as a functor from the category, from this to profinite groups. And GQ still injects in it, of course, because you have P1 minus 3 point. And now it's a beautiful theorem that here, this is indeed an isomorphism. So this has been conjectured by Hihara and by Oda and Matsumoto a long time ago, and it was very shady. There have been all sorts of stories on this, but now I think I can safely, almost safely, maybe Yukatsu will tell me, I can safely say that this is almost available in written form in Pop's papers, and also in Aaron Silverstein's paper. So it took like, I don't know, this was conjectured 1992, I mean 20 years ago. And well, it was a complicated situation. I mean complicated mathematically, and it was never written down and blah, blah, blah. But now I think you can safely say that it's true. And you can have a much smaller sample actually of varieties. You can actually confine yourself, for instance, to quasi-projective surfaces, that's plenty. So GQ is the outer automorphism group of the geometric pi1 functor over, if you take a sufficient number of varieties, sufficiently large sample of variety, and not very large in fact. But of course you cannot describe, this you can say is a geometric, so if you're very, very optimistic and highbrow, you say, okay, this is geometric description of your Galois group. But what do I do with this? Nothing. This is a description, but you cannot do anything with it. Now, if you take a very limited sample, which the one Grothendieck pointed out in the esquisse, namely all the moduli stacks of curves, and with their arrows and so on, then you can describe this. You can describe the outer automorphism group of this. And you get a group which is defined by 3 equations. Okay? 1, 2, 3, 4, well, actually 4 equations, but maybe some are even too many, I don't know. So it can be described, and there is a Lego. Maybe I should mention that there's a really beautiful Lego of this action. You can actually really compute many things on the action. There's what we call, I mean, what Grothendieck called the Teichmüller Lego, and it works, and we did it with Nakamura, who doesn't seem to appear. And so you can say many things, but you cannot say that you have actually pinned down the Galois group itself. It is still possible. I would certainly not bet on the fact whether this is an isomorphism or not. So, okay, I said 1/3 of what I intended to say, but I'll stop here.
Thank you very much. Any questions?
Could you be a bit more explicit about M-bar? You say a diagonal of these modular space stacks and
You mean this?
them? No, that one.
Oh, this.
To be precise, so the geometric one with the right is the outer automorphism group of a functor, right?
This one, yeah.
Is a functor.
Yeah.
Is that
outer because you land in profinite groups, so you can do.
Is that other one? Is that a functor, or is it an inverse limit of profinite groups?
No, it's not exactly an inverse limit because it's.
Or a limit.
Yeah. Well, first it's a diagram. It's a diagram.
Okay, so you keep the functor. You don't take the.
Yeah, it's the same functor. No, you keep the diagram. No, you don't take the limit.
Confusion. Okay.
Yeah.
Second, could you be a bit more
I
explicit?
see homotopy theories coming in.
And so could you be a bit more explicit about exactly which maps are in the diagram? So
They're called Knudsen maps. So they're quite explicit. So normally, I mean, actually, you have no. To be completely honest, to be completely honest, sorry. You can say something much stronger than this, which will maybe amaze you. Namely, that this is just out pi 1 geom. This I don't know exactly how to. I mean, I don't know how to prove 100%. This is it. So it's so simple that you don't need anything.
I don't need any maps.
No, you don't need maps. That's something we discovered. You avoid everything because this is 1, 3.
So how does it relate to the 0, 3? I mean, no.
Sorry?
Basically, before we had that it was all, I mean, and that a GQ mapped into out of F2,
Yes.
which was essentially pi 1 of.
Yes. But you can also map it into the automorphism group of pi 1 of geometry, or the geometric pi 1 of anything, especially this one. Okay. And the statement is actually this is equal to this.
Right. But then why do we know it's an injection? I thought we knew this was an injection.
Oh, because because first, if this is equal to this, and this is an injection. By sheer logic. I suppose, this is one possibility. No, the fact is, the maps, in some sense, the maps are not needed. That's something we also, I should say that there are many, the people who are maybe closest to do these kind of things are more Hoshi and Mochizuki in their anabelioids and what they're doing now, which is very hard to read, which I have very partially read. And they're not really concerned exactly with these spaces, but they're also agreed that the maps are not needed. The maps are inbuilt. So they're not, you don't need to mention them explicitly. What I just said was, okay, the thing that Grothendieck said and so on and so forth, but actually this is much stronger. I completely believe that this is all you need. One space.
So it's 1, 3.
1, 3. 1, 3 is a very beautiful space which I've not very much investigated, but you see, if you want to dream, maybe I'll return just, if you give me, no, it's too long. That's true.
I mean, the biggest question, I think, is why don't you mean M04 then?
I know, M04, no, is F2 hat. That would be much, this, again, you would return to out of F2 hat. The magic of it is that you have M05 sitting over M04, and this you have F2 hat, and here this is a semi-direct product of F2 hat and F3 hat. This is an extension of, actually it's a split extension of F2 hat by F3 hat, and all the magic of the thing is that this pins down whatever happens in the whole tower, in the genus 0 tower, to be honest, to be precise. Okay? To be precise, this pins down everything which happens in the genus 0 tower. For instance, out of Bn hat equals out of B4 hat equals GT. That's the theorem.
So where Bn is the break group.
So where Bn is the usual break group. So since for the M0n's have fundamental groups which are very close to the Bn's, you can prove this. Okay? So these are stability results, and all these stability results, which were first started by Hihara not in this context, in the linearized context. Linear meaning L-adic or pro-Neoplaton, which is the same. All these results, I'm not saying they are corollaries, but they are avatars of the two-level principle. So they're not corollaries. It doesn't. I don't mean to say that you can prove all these results using Grothendieck's geometric interpretation of the two-level principle. But they're avatars of that principle. So here is one. This one is, to be honest, not completely written down. But, okay.
So kind of M11 played no role in the story.
M11, not so much now. I mean, yes, well, M11 from this point of view is very much like M04. But maybe I should say that what people do on elliptic associators and so on, I mean, starting with Benjamin and so on, is more on the braid groups in genus 1. Okay, they look at the, when you go to the pro-nilpotent completion, you don't go to the MGNs, you go to the braid group, to the surface braid groups. So you have an exact sequence, like, say, 1 BG N, which is the braid group on N strand, gamma G and gamma G, 1. Okay, so you have a, so what people are doing now is more, look at this, for G equals 1, because G equals 1 is very special, you have, here you have SL2Z. If you don't put SL, if you don't, in Teichmüller theory, things become very, very, I mean, much more difficult when G is strictly bigger than 2. G equals 3 is the thing which determines everything. Well, sometimes. But no, I mean, which is very difficult. We don't know much about gamma 3.
Okay, no other questions? Well,
my question is not so important, I think. You wrote in the first line, Grothendieck system program.
Yeah.
Is it really 1983?
First, I don't know when he wrote it. Maybe it's 1984.
Oh, okay.
I think it's 1984. You know, it's the famous story that he wrote it in order to apply for a position in the CNRS, and a very menial one, saying that he wouldn't take such a costly position for himself, and he would be very happy to, I don't know, become a cleaning lady, and if only he could be accepted, it would be very good. And he wrote this program as part of his file application.
Did you get it?
Oh, that's a long story. Yes, in the end he got it. But there was a fight. There was a fight, and yeah, a justified fight. Is it useful to pay somebody who will never set foot and never talk to anybody, or is it more useful to pay somebody who may not be a genius, but he will be very useful to the community? That's something which cannot be decided.
Depending whether he's cleaning the toilets or not.
That cannot be decided. I leave it to you. But in the end, yeah, he got something.
yeah, little problem that we went a bit over time. So how important is it to finish in time? Should we have the break like half an hour now? Yes. So we start at 1:45. Yeah. Okay.